Okay guys, so we'll be continuing on seeing from where we left in the previous lecture. So in the previous lecture we had two partitions. Initially the gases were only present in the first partition, then we opened up a small hole in the partition, and then we'll allow the gases to just diffuse themselves from partition from chamber 1 to chamber 2. Okay, so from that thing we can write that the mole percentage of the lighter gas increases in vessel 2. Okay, mole percentage of lighter gas increases in vessel 2 or partition 2 or chamber 2, whatever you want to call it. And why is this the case? Because we know that R1 upon R2 for the two gases rather, A and B, we took in the last lecture, in the last example, the ratio would be root of m2 upon m1. Hence we can say that mole percentage of the lighter gas would increase. Why? Because R is inversely proportional to root of m. Okay, so more the mass of a gas, lesser would be the rate, and lesser the mass, molar mass of the gas, more would be the rate. Hence the mole percentage of lighter gas would definitely be more in vessel 2. Now let's look at another example. Suppose we have these two vessels. Okay, initially we have n1 moles here and 2 moles of B. Okay, so n1 and 2 are, rather we can directly write n1 upon n2, which would mean that it is the initial uh, ratio of gas A and B in terms of moles. Okay, and finally we have n1 dash of A and 2 dash of B in the second vessel. So we can write that n1 dash upon n2 dash would be effused mole ratio of A and B. Okay, so we can write that n1 dash upon n2 dash, obviously they are diffusing or effusing at the same point of time, so time does not matter here, would be equals to n1 upon n2 root of m2 upon m1. Okay, please remember this. We have discussed the same form multiple times, so by now it should be clear to you guys. Next, let's see enrichment factor or separation factor. Okay, so suppose we have vessel A, we have n1 moles of A and 2 moles of B. Okay, so now we have first step 1, wherein we have n1 dash moles of A here and n2 dash moles of B here, and thirdly let's say we have n1 double dash moles of gas A and n2 double dash moles of gas B here. So this is step 1, this is step 1, and this is step 2. So we can write that for step 1 we can write that the ratio of n1 dash upon n2 dash would be n1 upon n2 times root of m2 upon m1, and for step 2 we can write that n1 dash upon n2 dash would be nothing but n1 dash upon n2 dash root of m2 upon m1. Okay, I hope you can derive the equation for step 2, because step 2 means the third vessel would actually, the molar ratio of gases in the third vessel will be dependent on the molar ratio of the gases in the second vessel, and that is n1 dash upon n2 dash. Okay, so where obviously m1 and m2 are the molar masses of both the gases, so from both steps we can write that n1 double dash upon n2 double dash would be equals to, put the value of n1 dash upon n2 dash from step 1, we can get that it would be equals to n1 upon n2 times root of m2 upon m1 whole square. Okay, so this is for ratio for the gases in after the step number 2. Similarly, for step number 3, if that could have exist, or if that would have existed in this case, it would be molar ratio would be n1 triple dash divided by n2 triple dash would be nothing but n1 upon n2 multiplied by root of m2 upon m1 whole cube. That would be the ratio for step number 3. Similarly, for any random step we can write, or for any general step we can write that n1 for that step divided by step n divided by n2 for that step n. This is not a power, this is just a superscript, would be equals to n1 upon n2 root of m2 upon m1 raised to the power step number, which is n. So just remember this general form. Okay, and we can write that mole percentage of light gas, or rather lighter gas, increases in the effused gas mixture. Okay, so how are we saying that? Because obviously n1 and n2 were the initial moles, those are remaining constant, but when we are seeing m2 upon m1, then obviously let's say m2 was the weaker or lighter gas and m1 was the heavier gas, so moles of rather n1 upon m2 after step n would be, you can derive the mathematical relation and you can verify the same. Okay, so in this case, whether n1 and n2, you can just directly say that whether n1 is the moles of heavier gas and n2 is the moles of weaker gas or lighter gas, then we can say that n1 upon n2 would be multiplied with m2 upon m1. Okay, so the molar ratio of the same you can just calculate with the same thing. So let's you can just take an example and verify from the same. Okay, so I will just do the same. So if you guys are in any doubt, so let's say n1 was the moles of lighter gas. Okay, so this implies that m2 would be more than m1. Okay, so n1 after step n divided by n2 over after step n would be equals to, as n1 is the moles of lighter gas and initially let's say n1 was more than n2. Okay, so let's say n1 upon n2 initially was 5 upon 1. Okay, and let's say m2 upon m1 was, let's say, also 5 upon 1. Okay, so we can write that n1 upon n2 would be after five steps would be, let's say n was equals to step n was step number 5 we are talking about. So let's say n1 upon n2 was 5. Okay, and under root of m2 upon m1 was again 5 to the power of n. So as n increases, n was in this case 5, but as n goes to 6, 7 and 8, n1, the moles of n1 after step n divided by moles of n2 upon step n would actually increase more and more, and n1 upon step n divided by n2 upon step n would be nothing but ratio of moles of lighter gas divided by ratio of moles of heavier gas. Okay, so this was just an example to validate this statement. Okay, let me erase it out. Okay, so next we'll be talking on the initial and the final chambers, wherein in initial chamber we have been given n1 moles of A and n2 moles of B, and in the final chamber we have again n1 dash moles of A diffused and n2 dash moles of B diffused. So in this case we'll have something like initially we had n1 moles of A and n2 moles of B. Okay, this was the initial case, and then finally we had n1 dash moles of A and n2 dash moles of B. Let alpha be the steps to get from initial state to final state. So let alpha steps are required. Okay, and in that case n1 upon f, n1 raised to the power f. So not raised to the power, this is the step number f. So let alpha, or we can also write f number of steps, number of moles in step number alpha, and n2 superscript step number again alpha would be equals to n1 upon n2 root of m2 upon m1 to the power alpha. So we can write that, as we have seen that as the number of moles of gas of the lighter gas is continuously, more percentage of the lighter gas is continuously increasing as we increase the number of steps. So in a way it is getting enrichment of the mixture. Okay, the enrichment of the mixture is taking place as we are continuously getting more percentage of lighter gas in as we go to more number of steps. Hence let's say enrichment factor is F, and enrichment factor is defined as molar ratio after the alpha step divided by initial molar ratio, which should be equals to root of m2 upon m1 after alpha steps. Okay, so if we take log on both the sides, we can write that log of f is equals to we can write alpha by 2 here and log of m2 upon m1. Okay, so this is the equation which we get. Okay, so I hope you can simplify this logarithmic from logarithmic function, that it would be written as alpha times log of root m2 divided by m1 and alpha times log root of m2 divided by m1 raised to the power half, which can be further written into alpha by 2 log of m2 upon m1. So, okay, so this is just a rough part. Okay, so when we talk about the graph of the same, we can draw the graph as log of f and log of m2 upon m1 on the x-axis. Okay, so slope would be a straight line, nature would be a straight line, and slope would be nothing but alpha by 2. So with this we come to the end of this lecture. In the next lecture we'll be seeing more on the comparison of rates of diffusion of two gases. Okay, so till then, good luck and goodbye.